All right, so today we're talking about applications of real-world problems. And last time we did exponentials. Today we're going to be talking about logarithmic equations instead. So situations where we're going to see logarithms in real world is whenever you're talking about like earthquakes, like the Richter scale, sound, so like decibels, decibel measures use logarithms. Brightness of stars is actually something that uses logarithms as well. It's just kind of weird to think about, like how dim or bright a star is that you see in the distance. And then pH balance, which is a measure of acidity and alkalinity. So chemistry will see logarithms from time to time. Our first example, the Richter scale is used for measuring the magnitude of an earthquake. So the magnitude is M, and it's related to the released energy. The energy is the letter E in joules by the equation. Now, this first example says, how much energy was released by the Great San Francisco earthquake of 1906 that measured 8.2 magnitude on the Richter scale? So that 8.2 is our M value. So what we'll do is we'll do log base 10 of E equals 4.4 plus 1.5 times 8.2. And we're going to figure out how much energy was created by the actual earthquake in 1906. First, we're just going to do 1.5 times 8.2, and then we're going to add the 4.4. And we get 16.7. Now we have log base 10 of E, so we have to undo the log. So we want to do like a base 10 of both sides. And E ends up equaling 10 to the 16.7 power. And if we want to put that in scientific notation, we can. We just literally put in 10 to the 16.7 in our calculator, and it's going to give us something that looks like 5.01 times 10 to the 16th, and then we'll put J for joules. So that's how much energy it produced. Now, I don't know, I'm not very good with energy being measured in joules, so it's hard for me to say that that's a very strong earthquake, but I can look at the magnitude and see 8.2 and say that is definitely a very strong earthquake. The joules don't make as much sense to me in my head, but magnitudes do. But for you, maybe neither of them make too much sense. But anyway, with magnitudes, we're going to look at how strong can an earthquake actually be. And that's what part B is going to discuss. It says the Richter scale is often misunderstood. In most cases, this is the result of having little or no understanding of the logarithmic nature of the scale. So for example, what does the difference between a magnitude of 1 make in the release of energy? So difference of magnitude of 1. What's that going to do to change the earthquake value? So like let's look at two different magnitudes. We could say 4.0 magnitude. We'll look at and a 5.0 magnitude. And we're going to compare our results to try and figure out what's the difference in energy being released from a 4.0 to a 5.0. So 4.0, it's going to be log of E equals 4.4 plus 1.5 times 4. And what do we get? 1.5 times 4 is 6, so it should be like 10.4, I think. Yep, 10.4. And then we take a base 10 of both sides to get rid of that logarithm. So it's 10 to the 10.4 power is our energy. If I did the 5.0, same idea. And this time I end up getting 11.9 over here. And my E is going to be 10 to the 11.9 power. Now I can plug that in and make it scientific notation, but for this particular problem, when I'm just trying to compare the two, I'm going to look at the energy of the 5.0 earthquake divided by the energy of the 4.0 earthquake, and really see what the difference is between the two. How much stronger is the 5.0? So it's 10.4 there. And I do 10 to the 11.9 divided by 10 to the 10.4. And I get something like 31.622. And that number might not mean anything to you, but the trick with these real world problems is trying to figure out what does that mean. So we're dividing the strength of one earthquake divided by the strength of another. The energy of one earthquake divided by the energy of another. So for this one, we're saying this is 31 times stronger. So for this problem, by the way, this is log base 10 of E. E is standing for energy. It's not log base E. Okay, that's a very important thing to notice. If it was log base E, it would be a lowercase e. So, I'm sorry, we're going to say not this earthquake, we're going to say the 5.0 magnitude earthquake is 31 times stronger than the 4.0 earthquake. Okay, so the 5.0 is 31 times stronger than the 4.0. That's what this problem is telling us when we compare a difference of magnitude of 1. And it doesn't matter what numbers we picked. If I picked a 6.0 and a 5.0, I'd see that 31 as well. If I picked a 7.0 and a 6.0, we're going to see that there's always about 31 times stronger when you're going up one magnitude level, one entire magnitude. Okay. Let's move on to example 2 real quick. Then we'll take a little breather after this one. This one says the apparent magnitude of a star is the measure of the brightness of the star as it appears to observers on Earth. The apparent magnitude m of the dimmest star that can be seen is given by this equation, where d is the diameter in millimeters of the telescope's objective lens. It says if a telescope can reveal a star with a magnitude of 12, what's the diameter? So we want to figure out what is d in this case. So we're going to kind of work backwards to solve for d on this particular problem. And we're going to figure out what's the diameter of the star in our lens when we're looking at it through our telescope. So we start by subtract 2 from each side. I'm going to divide both sides by 5, and I get 2 equals log base 10 of d. I don't write base 10 though, I don't need to because it's just not written there. And now I have to undo a log, so I'm going to do base 10 on both sides. And this side becomes d, and the other side is 10 squared equals 100. And our units were millimeters. So once we come up with an answer, we just solved for d here. We have to look back at the problem and say, well, what was the d telling us again? It's the diameter in millimeters of the telescope's objective lens. So we're saying the star is 100 millimeters in diameter when viewed through the lens. And that's the idea for this particular problem. All right. So we got one more problem here. It's Newton's law of cooling, but we're going to take a little breather first. Let's go ahead and look at the last problem here. Oops. So the last problem, Newton's law of cooling for cooling a substance with an initial temperature T naught. So whenever you see like a little 0 next to it, it's like the starting value, any variable. So that's our starting value. In this case, it's the initial temperature. And it says the initial temperature T after T minutes. That gets a little confusing because the lowercase t is representing time. And not just any type of time, but minutes specifically. So that's what the lowercase t is. So this problem says you're driving on a hot day when your car overheats and stops running. Your car overheats at 280 degrees Fahrenheit, and it can be driven again when the car's engine gets down to 230 degrees Fahrenheit. So I give you this R value, which is just like an arbitrary number, but it's going to go in here to help with the equation. And it's 80 degrees outside. How long in minutes do you have to wait until you can continue driving? So what that means is we're trying to figure out, we got this initial temperature, we've got the outside temperature, and we've got the final temperature of the car before we can start driving again. So the temperature of the car needs to be 230 degrees. That's the final temperature. It overheats when we get to 280 degrees, and the temperature outside is 80 degrees. And if we plug in all the variables, the only one that we're missing is the time. And that makes sense because the question's asking how long in minutes, so how much time do we have to wait? And now we can go ahead and solve this equation. I'm going to say this is 200 times e to the negative 0.0048t plus 80. We'll subtract 80 from both sides. We're going to get 150 equals 200 times e to the negative 0.048t. Divide both sides by 200. We're going to get that base and exponent by itself. 150 divided by 200 is 0.75, or it could be 3/4. That's the same thing. And now, because I have a base e, I want to take the natural log of both sides. And that exponent's going to drop out in front. Natural log of e just becomes a 1, and the other side is still natural log of 3/4. And then the last part, I'm going to divide by negative 0.0048. So there's my exact answer, which exact answer in an application problem, that doesn't make any sense. So I do need to put that in my calculator. And I get something like t equals, I think it was like 59.9 minutes or something. 59.9. So we can say it will take approximately 60 minutes before I can drive again. The big thing with these application problems is don't get caught up. Like if I give you a formula and tell you to plug in some numbers, just really hunker down and think, where do these numbers need to go? That makes sense for the problem. And when it's asking for an answer in minutes, like make sure the answer makes sense. Like if I got like 3 million for t, says it's going to take 3 million minutes for the car to cool down, I might be waiting a long time. That doesn't make a lot of sense. It's got to be a realistic number, right? Someone's car isn't going to take 3 million minutes to cool down. It's maybe going to take an hour or two. And that's what this is showing, 1 hour. 1 hour later, it'll be ready to go. Okay? So as long as the answer makes sense to you is important. Make sure you go back and look at it and try and put it in the real world context of the problem. All right? That covers the lesson for today. Before I let you go, though, I do want to talk about the test next time.